Welcome to the first session of the working group meeting, and we're very pleased to have Josh talk about constructing inverse diagrams in homotopical type theory. An update.
Yes, wait for me to get this on. All right. Good morning, everyone. I am very grateful to be here. Thank you for having me. Can you hear me okay if I speak this loudly? Okay, cool. Yeah. Pointer, good. All right. Yeah, so I'm here to talk about some work I've been doing with Nikolai Kraus on constructing inverse diagrams in hot homotopy type theory, but also a little bit more generally, we expect in homotopical type theory, which is basically MLTT without the uniqueness of identity proof. So we expect we can do this without assuming univalence. Can I do that? Yeah, great. Okay. So first of all, what's an inverse diagram? An inverse diagram is simply a functor from an inverse category. So I need to tell you what an inverse category is. And the idea is basically these are categories where arrows go downwards in a well-founded way. So an example is the natural numbers, omega, well, as an ordinal, ordered backwards, if you like, where between any pair of natural numbers, there's one arrow going from the bigger one to the smaller one. It's well-founded because, of course, everything ends at 0. Another example of an inverse category is the flat natural numbers. Now you take the naturals just as a set, and you add an initial element. And so this, of course, all arrows go downward from the initial element to, well, any natural number. It's well-founded. And an inverse category that we really like is the opposite of the semi-simplex category. So this has various combinatorial descriptions. I like to think of it as this geometric thing of objects are n tetrahedra, and it's generated by morphisms from n tetrahedra to n-1 tetrahedra that basically correspond to the n-1 faces. Okay, and they compose in a nice way. You take a face of a face, that gives you a codimension 2 face of a tetrahedron. Okay, so these are examples of inverse categories. Now, why do we want to consider inverse diagrams? Why do we want to consider functors out of these things? So they give us pre-sheaf models of hot, of course, the Simplicio and cubical set models, well, plus extra structure. They can also be used to construct not just pre-sheaf models, but other kinds of, should I say pre-sheaf models? Yeah, pre-sheaf models, not just into set, but also into other categories. They give you parametricity and homotopy canonicity results. So these results are, for example, by work of Schoeman and Kapolkin and Lumstein. And finally, as well, it's well known that they are used as building blocks for higher and infinity categorical structures. And I mentioned in particular something by Joachim Koch, who uses, in fact, inverse categories to construct higher categories with strict associativity. So yeah, the point is basically that if you're studying type theory, why should you care about inverse diagrams? Well, they give you both meta-theoretic applications as well as, well, applications in sorry, yeah, they're relevant to both meta theory and applications of type theory. Okay, right. Right, so what's the idea? An important idea is that if you look at an inverse category and you take those that are called simple, which I will define in a moment, then the co-slices of these inductively encode contexts which tell you dependence. Well, they encode dependency contexts of things. So first I'll quickly tell you what a simple inverse category is. So first of all, well, I'm going to talk in this talk about countably simple categories. Countably many objects, basically. So we have an isomorphism from the objects of the inverse category I to the natural numbers, and so this induces an order on the objects. It's inverse, so if there's any morphism from I to j, then I is larger than j. Morphisms only go downwards. And this has this finite fan-out property, meaning that if you look at any object and look at the co-slice under it, this co-slice is finite. So in particular, all the Hom sets are finite. Let's see, so inverse and having finite fan-out are what Mackay, in his work Folds, calls simple inverse categories, and so we consider a countable version of these. Examples include, as we saw before, from before, omega op, so this sequential downwards natural numbers, the semi-simplex op category. The fat natural numbers are not simple because, of course, like the code slice under the initial object is not finite, it's countable. The face maps of the cube category also form a simple, countable, simple inverse category. Okay, so I say that the point is that code slices of simple categories encode dependency contexts. And how does this work? Well, so here is an example of an initial segment of an inverse category. It's simple, trust me on that. And here I've drawn out explicitly every arrow. All the triangles you see in this diagram commute, but this square marked with the X doesn't, okay? So implicitly, they are relations. So like, for example, this triangle here and this other triangle here, they both commute, sure. Okay, what's the idea? Well, we go level-wise on the ordering of objects and build up context, basically. So at level 0, you look at the code slice. Oh, I should say, first of all, that I'm ignoring identity arrows. Properly speaking, you take the truncated code slices, or you work with semi-categories. Here, I just sweep this under the rug a little bit in this talk. You take the code slice under 0. It has no dependencies, so the dependency context is empty. Now, inductively, if we assume we have type A0 in the empty context, now we look at level 1. The code slice under 1 consists of one arrow, and the point is that arrows correspond to variables. So here we have a variable, single variable x corresponding to the single arrow. Its codomain tells you what its type is, and so we have a context x of type A0. Okay, so that's the dependency context. Now we do this inductively. If we assume we now have additionally an A1 in this context, look at code slice under 2. Now there are 3 variables corresponding to the 3 arrows. There's an x, codomain A0. The next one is a y. Now it has codomain 1. And this one has a dependency itself based on, this arrow here in the code slice. What's its dependency? Well, you compose that to get x. So that's where you get the x there. And this is the way it goes. Similarly, z, because both triangles commute, get x as well. Cool, so we do this basically. Here we have the same thing as in the level 1 case. And finally here, this is complicated, so yeah, you do this in this well-founded way. So x, well, there are 2 arrows into 0, there are 2 variables of type A0, and so on and so forth. Now you do this 1 into 1, you look at its dependencies. Here, z is of type A2, depending on this arrow, and that arrow. This one composes to x0, which is the first thing here. These 2 each compose to y. Yeah, that's how it goes. Okay, so this is the idea. Right, so remember I talked about constructing inverse diagrams. So what does this have to do with inverse diagrams? The idea is you sigma everything up. So here we have these dependency contexts, mi. If you sigma these up with what you assume you have, these types and contexts, now you get an inverse diagram. And so if you look at, take the initial part of the diagram I drew, of the category I drew previously, and look at level 2. So here we sigma up A0 with the empty context, and you just get A0. Sigma up A1 with its context, so this is the sigma of A1 and A0 and A1. And here you sigma this up. Okay, so this is the action on objects. So how do you get morphisms? How do you get an actual diagram from this inverse category to this one? The idea is that morphisms are now actually just definitionally given by projections out of your types. Right? So you project out the appropriate components. So for example, here you get the first one. These 2 things just get sent to first projections. This one is a quadruple of x, y, z, and something that I don't care about. You project out, well, this arrow here corresponded to the variable y, so you project out y with its dependency, and similarly here you project out the variable z with its dependency. And the point is that the relations on compositions in here are definitionally satisfied just by this. You don't have to go and add in propositional equalities saying that these things commute. Okay, so this strategy, this way of drawing diagrams, I guess, of encoding diagrams, well, you get what are called strict redifibrant diagrams X in type theory. And these MIs that we took all the pain to construct so that we could get this definitional stuff called the matching objects of the diagram X. Okay, so, right, so in general, oh, there's a clock. In general, when we think about inverse diagrams in the literature, it's very often done in a classical mathematical meta theory. Well, sometimes constructive, but generally just a standard categorical context. And very frequently, we take the codomain category to be the category of sets. What we want to do in this current work is change our meta theory to be homotopical type theory, which, as I indicated before, includes not just hot, not just homotopy type theory, but also just Martin-Löf type theory, where you just don't assume UIP. And we very often want to replace the category of sets. Actually, let me not jump ahead of myself. First of all, we take C now to not just be any regular category, but a wild category, which is a relaxation of a very vast generalization, I guess. It's a pre-category where the hom types are now not required to be sets, just arbitrary types. So this is a very wild, very ill-behaved notion of a category. So the reason we want to do this is because we very often want to replace the notion of set in this context with a universe in our context. And the universe type can be seen as a wild category of, well, the U-small types and the functions between them. Of course, now functions between any two types don't form sets, and this is why we take this generalization. If you know something about this stuff, you will know that really what we want is to consider a notion of infinity category inside hot, but this is an open problem. So this is currently one of the better things we can do, one of the best things we can do, let's say. And in fact, the reason we do this is because, well, we are aiming to work towards at least understanding the situation. How do we actually get up to maybe being able to talk about infinity categories in homotopical type theory? So the reason we want to do this, change this setting, is that we want to now do, for example, meta theory as well as applications of these inverse diagrams completely internally to hot. So this gives us internal meta theory of type theory, as well as higher categorical structures. At least that's the goal. Okay, right. How am I doing on time? How much time do I have? And didn't see when we started. Yeah, okay. Right. So technically, what is it that we do? So we want to construct inverse diagrams. Well, we want to construct these things, inverse diagram functor to from an inverse category to some wild category C. And we place a bunch of, well, restrictions under which we work. So we want to take simple inverse categories I, and we want to construct functors into wild category C, where for technical reasons, let's say, we additionally ask for a CWF structure on the wild category, which has pi types, and a, let's call it a universe. But when I say universe here, I don't mean like a universe with a, so I have a decode function, but I don't have, wait, which one do I want? I have an EL, but I don't have a, it doesn't classify types, basically. Yeah, so it's not an object classifier, but it's just a source of types. So given these two things, which we can define in hot, we want to define diagrams from I to C, and we do it by, well, this involves constructing matching objects of these diagrams. What does nice enough mean? Well, for us, in our current strategy, we take our simple categories to be what we call strictly oriented. For now, just black box this. I won't yet tell you what this means. What's more interesting, of course, and more difficult is what does nice enough wild category mean? So of course, if we set truncate the wild category, you just get the regular category back, and you can essentially reproduce all the theory that has already been done. So set truncated is certainly nice enough, but we're keeping this possibility, we're not taking this possibility yet. We're keeping this open, and we're asking, well, let's just go through, just take a wild category, do our construction, and see what coherences come up that we need to then impose. So we are doing this on a piecemeal basis, let's say. We go through, do the construction, see what coherences we need to place on the thing. And maybe at some point we will need set truncation, but who knows. So another possibility for nice enough is, well, probably not, but maybe uniformly coherent somehow. Let's see. I'll spoil it right now and say that we haven't finished this yet, so I don't have a big punchline at the end. Okay, but how do we do this in type theory? Well, we essentially copy the strategy, the process that I showed earlier. So being a bit more precise about this, the matching objects are indexed over, we looked at these co-slices under objects, and we did this in a sort of a level-wise, well-founded way. So what this means is that there's a filtration of each co-slice, a truncated co-slice, let's say, by, again, I'll black box linear, by a certain kind of co-sieves. So if you recall here, first we started with just the empty thing. We want to define the matching object M2. So we look at this first arrow down into 0, we get the variable x, and then we look at this one and get the variable y, and then we look at that one. So this gives you a filtration of the final co-slice under 2 by a sequence that looks like that. Yeah, so now when we copy this into type theory, well, we can organize linear co-sieves into a strict category, which will then let us, well, do the construction. So the idea is that linear co-sieves of strictly oriented I form a category Li, and this category looks like, well, I'll tell you what it is in a moment. And there is a split by fibration out of this category back into the original inverse category. So what is Li? Well, Li is basically a category of co-sieves, but we impose bounds on the height of the co-sieve. Okay, so there are 3 things I haven't told you about. I asked for your patience, just black box them. I haven't told you what a strictly oriented inverse category is. That's just some niceness property. I haven't told you what a linear co-sieve is. For now, just think about them as being, well, they look like well-founded orderings on arrows of co-sieves without gaps. And the height of a co-sieve is just a height, but yeah, okay. So what is this category L? It's co-sieves with bounds and a morphism. So I is the apex of the co-sieve, B is the bound on the height of the co-sieve, and so you get this projection functor that just projects to the apex. And then a morphism from some co-sieve to an SS to another co-sieve T consists of this data. Basically, it's an arrow between the apexes, such that the target co-sieve is a subset of the restriction of the domain co-sieve along that arrow. And we also require the bound to weakly decrease. Okay, this is a little bit abstract, maybe. The reason for this is basically, I'll write this first. Matching objects, as we saw earlier, actually, well, they should arise as wild functors from this category, L, to the wild category, C, that we are interested in. And the intuition is that the bound, let me do it here, right? The bound B here tells you how many of the types A0 up to AB you have assumed. And the S, well, that tells you the shape of the M that you're going to construct. Okay, so that's the intuition. We make this intuition precise by this theorem / construction that we are currently working on in AGDA. what does it say? Well, given a strictly oriented inverse category and a nice enough coherent wild wild category C with a pi and universe CWF structure, well, first of all, what we do is we construct another category from I called a category of shapes. And the idea, the intuition, yeah? Oh, great, okay, thanks. The intuition is that this category of shapes, let's say, approximates the category of coesives L over which we construct the matching objects. So if you recall from earlier, we constructed matching objects in this well-founded inductive way. Well, L is a category of coesives, and a priori, I mean, it's just like it's sets and membership of morphisms in subsets and stuff like that. So what we want to do is pick out a particular subcategory that has the structure that over which we can inductively define what we want. So the point is that there's another category, SHI, shapes, that embeds into the category of coesives via some embedding iota, which, first of all, is injective on objects. So you don't, I should say, injective on objects. Yeah, cool, okay. It hits every co-slice, so you don't lose anything in that sense. And it sends arrows to up-Cartesian lifts of this bifibration that I mentioned earlier. Okay. What's the point of this? Well, then by induction on the objects of this category, we can now simultaneously define the type of a generic diagram from I to functor from I to C, using the CWF structure that we placed on C. So we can define this together with a wild functor M from this approximation to the category of coesives, such that, well, because you did hit the co-slice over which we construct the final matching object, M, well, you take the inverse image of this thing, and this, in fact, gives you the matching object of the generic diagram that we want. Well, that's the idea. It's work in progress. And, well, the two big pieces of the work in progress are basically, well, so when we construct these diagrams from I to C, there are like two halves you have to worry about. You have to worry about how you're going to actually pull out the structure of the index category, and then you have to worry about coherences in the target category. So on the coherences in the target category side, well, we need to figure out, as I alluded to earlier, what sufficiently coherent means. Set truncated definitely is enough. So far, actually, we're up to maybe, let's say, 70% of the construction, and we haven't yet needed to use it, but of course, this kind of doesn't say anything. But the interesting thing is, as an investigation of where we will actually need a set truncatedness, that would be interesting to find out. And on the inverse category side, on the index side, we need to figure out the correct induction principle. So initially, when we first started this, we thought, oh, okay, we can just do it by induction on some triple of natural numbers and things. And this is not structurally decreasing, even though it actually does decrease by the fact that we're working in an inverse category. But it's not structurally decreasing, and so ACTA doesn't accept this. This is a bit of a pain because like our definition is huge, it has many components, it's all mutually inductive, so we need to figure out how to get ACTA to accept this. And this is kind of related to how we choose to define this category of shapes. So we're constructing this by induction over the objects. So how do we construct this? And how does it embed into the category of coesives? So yeah, that's the current state of things. I think that's all for now. Thanks for your attention.
Hey. Thanks, Josh. We have a couple of minutes for questions. Yeah.
Just a quick thing. Axiomatically, is what you're constructing there a comprehension category? So vibration where you have comprehension in the end?
Which part are you referring to?
Well, everything, I guess.
Oh, sure. I mean, yeah, so
you have the LI, as which is then the total category of vibration, right?
And
then
yes.
forming, that's kind of looks like the context
Exactly,
on one
right.
side, and then you have the comprehension to build the context from types in context.
It kind of looks like that. So, right, excuse me. So currently, this thing actually just came up sort of in the course of thinking about this. It's not actually what we're not deliberately constructing a model of type theory from this bifibration. It would definitely be interesting to figure out what's happening here, because one of the unspoken motivations of this work is to relate constructing internal models of hot to some other, to some other problem. But really, the thing that we have is we really focus on, we have this C itself is a wild CWF. So here you have, say, something that's maybe, that should be equivalent to some kind of wild comprehension category. But here this Li is on the index side, and here we, at the moment, are not looking at that. But I just stated because the point of bringing up the split vibration is that the arrows here, so when I said that SHI here, like approximates Li, so this is the point. The arrows in SHI get sent to up Cartesian lifts, and we're inducting along these basically. So very crucially, these things here, or at least the arrows that get, the arrows in SHI morally correspond to these up Cartesian lifts, and the arrows in SHI are crucial to constructing the matching objects. So there's a little bit of a, there's something interesting going on there that I haven't quite figured out yet. Yeah.
Okay, thanks.
No, I was just bringing it to you.
Okay, well, I think we'll take the rest of the questions for Josh in the break, so let's thank Josh again.